Hi, I'm Dial Holton, the Product Manager for Microcalorimetry at TA Instruments. Thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging windows to your liking. You can resize the video and slide windows independently from one another by clicking and dragging the bottom right corner of each window. If you get disconnected at any time, please use the instructions you've received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions, and if you need help at any time, click on the question widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these questions as possible at the end of the webinar. Our guest speaker today is Dr. Ernesto Freire. Dr. Freire is the Henry Walters Professor at Johns Hopkins University, where he is a member of the Department of Biology and Biophysics and holds a joint appointment in the Department of Biophysics and Biophysical Chemistry at the Johns Hopkins Medical School. Dr. Freire is a member of the steering committee of the Johns Hopkins Malaria Research Institute and the scientific director of the Institute of Biocomputation at the University of Zaragoza, Spain. Dr. Freire conducts research on drug design against HIV infection and other viral diseases, new antimalarials, anti-inflammatories, and inhibitors of protein-protein interactions. He has pioneered the development of drug design strategies using thermodynamics and microcalorimetric techniques. These strategies are aimed at achieving extremely high affinity, high selectivity, and superior resistant profiles. Dr. Freire is an unquestioned leader in this field and co-authoring over 230 publications, several patents, and serving on the editorial board of multiple journals and receiving several awards for his contributions to experimental thermodynamics. Dr. Freire is an honor member of the Spanish Society of Biochemists and Molecular Biology and a member of the Academy of Sciences of Latin America. It is a true pleasure to have Dr. Freire with us today. The title of his talk is Thermodynamic Rules to Achieve High Binding Affinity and Selectivity. Ernesto.
Thank you very much. I'm going to talk today about the use of ITC in the optimization of the binding affinity and selectivity of drug candidates. As we all know, drug candidates are first identified by screening large libraries of molecules. Those screening techniques usually produce molecules with binding affinity in the micromolar, mid-micromolar range. And for those molecules to become reliable drug candidates, their affinity needs to be optimized, needs to be increased to the nanomolar or subnanomolar range. That means that that molecule needs to have 5 orders of magnitude more in binding affinity, or equivalently about minus 7K cal per mole more in the binding free energy. Now, that task is not easy, and it's not easy because the optimization needs to follow very stringent constraints. Those constraints are basically designed to maintain the drug-like character of the molecule. For example, in order for a drug molecule to be orally bioavailable, the molecular weight has to be less than 500. The C-log-P, the hydrophobicity, cannot exceed a value of 5. No more than 5 hydrogen bond donors, no more than 10 hydrogen bond acceptors, and obviously no toxic groups. These are the famous Lipinski rules of 5 and have set the stage for the development of drug molecules nowadays. Now, prevalent approaches to optimize those compounds have resulted in more hydrophobic compounds. And that has been a problem, or still a problem, and a problem that is acknowledged by the industry. The same Chris Lipinski, for example, monitored the hydrophobicity of Pfizer drug candidates and plotted the hydrophobicity as a function of time, and he noticed that there was an increase of almost 1 order of magnitude. More recently, an analysis of drugs that are in the market versus new molecular entities reveal that of all the marketed drugs, 41% have high solubility and high permeability. However, only 5% of the new molecular entities have that characteristic. In fact, 90% of the new molecular entities belong to the low solubility or the low permeability class of compounds. And that's a real problem. Analysis of different drug candidates have revealed that high-quality compounds are those characterized by high affinity and small C log P. That is, compounds that somehow have achieved their affinity without invoking to hydrophobicity as a way of doing it. And that has been noticed, and a new metric has been established, which is called the lipophilicity index of the compounds, lip-E, which is the difference between the affinity, or the IC50, minus C log P, which is the hydrophobicity. Basically, how much of the affinity is not due to hydrophobicity. And that has been established as a metric. And in fact, there are different papers which mention that, for example, high lipophilicity or molecular weight are liability for in vivo performance, clearance, solubility, absorption, membrane permeability, etc. And that increasing lip-E, not just potency, should be the goal. So how can we achieve all those goals in an efficient, rational way if we have a compound that we want to optimize? Now, for that, we studied the thermodynamics of binding and analyze how the different thermodynamic parameters provide a rigorous foundation to all these empirical metrics that have been developed. If you remember, the binding affinity is given by the Gibbs energy, delta G, which in turn is a function of the enthalpy and entropy changes. We usually represent the affinity in terms of what we call the thermodynamic signature, the delta G, delta H, I minus T delta S. And that's a very visual, important way of looking at the binding characteristics of a compound, because in one single view you can have an idea of which are the dominant forces, enthalpic or entropic. And what we are going to do in the next minutes is try to unravel what are the forces that are behind the enthalpy and the entropy contributions to binding. First, I should say that the thermodynamic signature can be measured in a single experiment by ITC. As you know, in a typical ITC experiment, macromolecule is in the calorimeter cell, ligand or drug molecule is in the injecting syringe, and the titration is made. And the uniqueness of ITC is that measures binding in terms of the heat that is either absorbed or released during the process. And that allows to calculate not only the binding affinity, but because the observable is heat, also the enthalpy. And by using the thermodynamic equation, calculating minus T delta S. So one experiment gives you delta G, delta H, and minus T delta S. That's unique, and ITC is the only technique that can do that. Now, during the evolution of drug molecules, laboratories aim at several things: higher binding affinity, better selectivity, better resistance profile in the case of anti-infectives or also anti-cancer drug molecules, better solubility, better membrane permeability, etc. Now, when we analyze the evolution of certain classes of drug molecules that are in clinical use, what we realize is the following evolution. These are the approved by the FDA HIV protease inhibitor. And what we realized a while ago is that the original inhibitors were entropically driven, whereas the latest inhibitors are enthalpically driven. There is a change in the character of the thermodynamic signature. The very first inhibitors had not only enthalpies that were not contributing to binding, they were positive, meaning they were opposite binding. Whereas darunavir, the latest one to be approved, is strongly enthalpic, and the entropy contribution, while positive, is much less. So what are the differences? Differences are that the newest compounds have much higher affinities from nanomolar to picomolar range. They have much better resistance profile, selectivity, etc., which is what the scientists were after in developing these new compounds. Obviously, they didn't care about enthalpy or entropy, but it happened that the best compounds were those that had an enthalpic character. So the evolution from first in class to best in class appears to be related to the evolution of the contribution of enthalpy to the binding affinity. Statins, which are one of the biggest sellers, the inhibitors of HMG-CoA reductase, the cholesterol-lowering drugs, show exactly the same pattern, starting from the original one to rosuvastatin, or Crestor, which is the latest one, atorvastatin, which is Lipitor. You see a very, very nice progression towards higher enthalpy as the binding affinity also increases. Now, as I mentioned, it seems that the evolution from first in class to best in class results in more enthalpic compounds. So what is behind the enthalpic evolution of a compound? What are the forces that are behind enthalpy and entropy when we are engineering a drug molecule? Now, important contributions from an engineering point of view to binding affinity, that is, contributions that can be manipulated by the scientists, are desolvation. Obviously, a drug molecule as well as the binding pocket contain water molecules, and when the drug molecule binds, the water molecules are going to be released to the bulk of the solution. Polar groups are able to form hydrogen bonds, and according to how well the drug molecule fits in the binding pocket, van der Waals interactions will increase. Also, there are changes in conformation that are reflected in changes in conformational entropy. For example, if the drug molecule has rotatable bonds and is able to adopt many different conformations in solution, when it binds, it will be occupying a single conformation, and there will be a loss in degrees of freedom, conformational degrees of freedom, and that's a loss in entropy. The binding pocket also can suffer that type of restrictions in conformation. So let's start with desolvation. Desolvating a polar group carries a penalty because polar groups likes to be in water. And this table, which was compiled by Cavani a while ago, shows the desolvation free energy of different groups that are used in the optimization of drug molecules, amino groups, carboxyl groups, hydroxyl groups, carbonyl groups, etc. And as you can see, the penalty of desolvation is on the order of 5-6 kcals per mole. That means that if a polar group gets desolvated, goes inside the binding cavity without making any interaction, like if it were in vacuum, it will pay a penalty on the order of 5,000 to the binding affinity. On the other hand, non-polar groups, methyl groups, for example, like to get out of water. That's why they are hydrophobic. And the free energy of desolvating methyl group is on the order of minus 0.76 kcal per mole. So it's favorable to take non-polar groups, even if it doesn't make any interaction with the protein, with the binding pocket. Now, also I would like you to notice that the magnitude of the numbers associated with desolvation of polar groups, independently of the sign, are 1 order of magnitude larger than those of non-polar groups. The origin of the desolvation penalty is enthalpic. If we take, for example, an amino group, as we saw in the previous graph, the energy of penalty of desolvation is 6 kcals per mole, but the enthalpy penalty is 9 kcals per mole. And the entropy is obviously favorable because desolvation always releases water. That is a favorable process. On the other hand, the desolvation of non-polar groups, like the methyl group that we saw before, has a very, very small enthalpy penalty and obviously a favorable entropy change. Again, you can see the differences in magnitude between polar and non-polar groups. And that's a very important consideration, because when a polar group is introduced in the wrong position, it's extremely costly, whereas non-polar groups, the penalties are always minimal, if any. Let me give you some examples. These are 2 compounds, and I'm going to present pairs of compounds that vary in only 1 chemical functionality, so changes can be attributed to that functionality. And obviously, for example, in this case, we have a methyl group. And if we measure the thermodynamic signature, we see that the affinity improved by about a factor of 8. There is a small improvement in the enthalpy of binding and a small improvement in the entropy contribution. And that's typical for non-polar groups. Small improvement in enthalpy, small improvement in entropy, little by little. That's why it has been easier for scientists to optimize using hydrophobicity than polar groups. Common situation with hydrogen bond. Again, 2 compounds that are exactly the same, except that a methyl group is replaced by a hydroxyl group. In this case, the affinity improved by about a factor of 2, but we see the enthalpy goes from minus 4.8 to minus 9.2. So more than 4 kcals per mole of improvement in the enthalpy. But the opposite happens with the entropy. The entropy goes from minus 3.7 to 0.2. So almost a complete compensation of the gain. This is what is called enthalpy-entropy compensation. And also let you know that the magnitude of the changes in the case of polar groups are much, much higher than those observed with non-polar groups. So there are different factors that contribute to the enthalpy-entropy compensation. Desolvation, or lack of desolvation when a hydrogen bond is formed. But the most important one that we see in drug design is changes in structural degrees of freedom. For example, if a hydrogen bond is formed between a compound and in this case an aspartic side chain, we can have a gain in enthalpy that is compensated by a loss in entropy. And the reason for that is that the rotational degrees of freedom are lost when the hydrogen bond is formed. So in this particular case, we have a gain in enthalpy and a loss in conformational degrees of freedom. So that's why one of the recipes that we have prescribed is to target hydrogen bonds against structured parts of the molecule. Now, there are many ways of if the structure of a target is known, of evaluating which groups are well structured and which groups are not well structured. And starting with using the simple temperature factors in the crystal structure. For example, this is a binding pocket of a kinase, and you see that the bottom of the binding pocket is blue, is well structured, whereas residues at the surface are usually disordered. And that means that if a hydrogen bond is targeted to one residue that is disordered, probably what is going to happen is that that residue is going to be ordered by the hydrogen bond, and the gain in enthalpy will be lost by the ordering process. Whereas if a hydrogen bond is formed with an already structured region of the protein, the compensation will be much less, if any. So to summarize the main contributions to the thermodynamic signature, favorable contributions are hydrogen bonds and van der Waals interactions, favorable contributions to enthalpy. Favorable contributions to entropy are desolvation of compound and also binding site. And unfavorable contributions are polar desolvation. Any polar group that doesn't make a good hydrogen bond with the target protein is going to pay a penalty and is not going to contribute to affinity, will be detrimental. And that's one of the very first things that need to be eliminated. The other unfavorable term is structuring, and structuring of the compound, for example, that has been addressed by medicinal chemists for many, many years by conformationally constraining the compounds. If a compound has the same conformation before it binds, then the conformational losses are going to be minimal, and that structuring factor can be decreased. Obviously, if the structuring is due to the protein, that's a different story. So it's obvious that in order to maximize the affinity, we need to maximize favorable contributions and minimize unfavorable contribution. So with that in hand, we can ask ourselves again, what is the thermodynamic origin of lip E? So what is for example, when we go from indinavir to darunavir, one of the original HIV protease inhibitors, to the latest one, in which the enthalpic entropic character changes completely, we can make the assessment that in going from a non-enthalpic to an enthalpic compound, we are in fact increasing the lip E of the compounds. For example, if we calculate the lip E for all the protease inhibitors, we see that they are very nicely correlated with the enthalpy. The same for the statins, and the same for a series of compounds from the same chemical scaffold that is being optimized. Lip E and delta H are correlated. Also, I should point out that the binding enthalpy is not correlated with the number of hydrogen bonds. You can have favorable enthalpies and unfavorable enthalpies with exactly the same number of hydrogen bond donors. It's the question of where those hydrogen bond donors or acceptors are located. The trick here is repositioning the polar functionalities in the compound. So we have come out with 5 rules for affinity optimization. First is that enthalpic hits in screening should be preferred for optimization because, as we have seen, the enthalpic optimization is more difficult. If the compound is already enthalpic, that's a good start. Polar groups should establish strong hydrogen bond with structured groups in the target. Otherwise, the polar groups are going to pay the penalty of desolvation. Polar groups that do not establish hydrogen bonds should be eliminated because those are the source of unfavorable enthalpy. Non-polar groups should fit tightly in the binding pocket to optimize the van der Waals interactions, and losses in conformational degrees of freedom should be minimized. Those are the 5 rules that will result in a compound with extremely high affinity and good thermodynamics balance. Now, let's talk a little bit about selectivity now. And what we want to prove is that compounds that were enthalpically optimized or that evolved as best-in-class by enthalpic optimization, like the protease inhibitors and the statins, not only have much higher affinity, but better selectivity. Because enthalpic interactions improve selectivity even in those cases in which they don't contribute to affinity. And I'll give you some examples. Now, selectivity, first, it can be quantitatively described as the ratio of the KD to the off-target and the target molecule. If in that graph, the green molecule is the target, the blue is an off-target molecule, certainly we want our compound to bind only to our target, not to other molecules. And the more selective, the larger the KD ratio. That's the measure of selectivity. So what we've seen, and many other scientists have seen throughout history, is that selectivity usually increases with the affinity. And this graph, for example, shows the selectivity of thrombin inhibitor with respect to factor 10A as a function of the affinity towards thrombin. And you can see that there is an increase in selectivity with the increase in affinity. But we also see that there is a spread, about 2 orders of magnitude difference in selectivity, even at the highest level. As drug designers, what we would like to have are the compounds at the top, not at the bottom of that graph. That is the ones with the highest possible selectivity. How do we achieve that? How do we go up in affinity and also up in selectivity for the same affinity? There are 2 ways. One is that a chemical modification of the compound improves the affinity towards the target to a higher extent than to the off-target molecule. And second, that a chemical modification actually lowers the affinity of the compound towards the off-target molecules. I'm going to give you an example again with the HIV protease and 2 proteases, pepsin and cathepsin D, that are aspartic proteases in the human body, and those proteases need to be off-target. First, we look at the effects of improving the affinity with 2 hydrophobic groups. So we have exactly 1 compound in which R1 and R2 are either hydrogens or methyl groups. That groups are in a cavity in the binding pocket. The hydrogens don't fit the cavity well. With the methyl groups, there is an extremely tight, perfect fit. If we measure the binding affinity of these compounds, what we see is that the affinity improved from about 11 nanomolar to 0.14 nanomolar, almost 2 orders of magnitude in increase in binding affinity. Now, as I mentioned before, the increase in binding affinity is due to a slight increase in enthalpy and a slight increase in entropy. That's always the case. Hydrophobics, small increases. Now, if we measure the affinity of those compounds against pepsin and cathepsin D, what we see is that in both cases, in all cases, the affinity increases when we include the methyl groups. For pepsin, from 854 to 345 nanomolar. For cathepsin D, 139 to 22. Now, and obviously for the protease, the target, from 11 to 0.14. So the hydrophobic groups in this case have increased the affinity towards the target more than to the off-target molecules. And in that sense, the selectivity has been gained. And we can see that in the bar graph form. The arrow that goes down with the highest slope means that there is a larger increase in affinity to the target than to the off-target molecules. Now, we have another example. In this case, the R is either a thioether, that it cannot form a hydrogen bond, or a sulfonyl group that can form a very strong hydrogen bond with the protease. And we can see that the binding signature, the thermodynamic signature of the two compounds, are characteristics of what we observe when a polar group forms a strong hydrogen bond. The enthalpy goes from -8 to -12, 4 kcals per mole. And that's something that we see when a group forms a very strong hydrogen bond. Delta H is gains in the order of 4 or 5 kcals per mole. But you can see that the entropy, again, goes the other way around. There is a compensation, almost complete compensation. There is no gain in affinity. In fact, there is a little loss in affinity. The affinity goes from 13 picomolar to 20 picomolar. So the two compounds have very similar affinities, but very different thermodynamic signature. And that's a very nice example, because here we have a very strong hydrogen bond that does not contribute to affinity. Let's see how the hydrogen bond contributes to selectivity. When we measure against pepsin and catepsin D, we see that there is a big loss in affinity when the polar group is placed in the compound, from 197 to 2000, and from 90 to 1300. So there is a large drop in affinity for the off-target molecules, and there is an improvement in the selectivity, even if we are not improving the affinity with the hydrogen bond. And you can see that in this table. There is small change with the target, a big change with a big loss in affinity with the off-target molecule. And the reason is very simple. With the off-target molecules, the hydrogen bond cannot be formed as strong as with the target molecules, so the desolvation penalty of that group predominates, and that causes the loss in binding affinity. So here is some figures summarizing what happens. So if a non-polar group is added to the molecule, there will be a slight increase in enthalpy and slight improvement in entropy. If the group doesn't fit, still we have a slight increase in enthalpy and entropy, because the non-polar group likes to get out of water, even if the van der Waals are not perfect. On the other hand, if we have a hydrogen bond donors or acceptors that match the partners in the protein, we have gains in enthalpy. They could or could not be compensated by entropy. But if one of those, or the two of them, cannot be satisfied, then there will be a big loss in enthalpy, and the group will essentially pay the desolvation penalty. So up to now, I have summarized some thermodynamic guidelines, but how can we apply those guidelines in a practical way? And what we've done is develop this idea of the thermodynamic optimization plot. And the thermodynamic optimization plot is very easy to implement. All that is needed is a graph in which the y-axis is the enthalpy and the x-axis the minus T delta S. In that graph, we place the coordinates, enthalpy and entropy, of the compound that has been selected for optimization. And then we trace a line with slope 1. And that curve is going to stay. We are not going to fit, not going to do anything. So obviously, the chemists, the medicinal chemists, the organic chemists will synthesize analogs of the compound that has been selected, and those analogs will be measured again by ITC, and their coordinate placed in the same graph. And the characteristics are as follows. All compounds that fall on the same line have exactly the same binding affinity as the original compound, except that they have different enthalpy entropy combinations. So the one at the bottom of the orange compounds is going to have the highest favorable enthalpy, and the one at the top, the lowest. But all of them have the same binding affinity. Compounds that fall on top of that line, above the line, have lower binding affinity than the parent compound, and compounds that fall below the line have a better affinity than the parent compound. So up to here, very simple. We've done what everybody will do if you know what the binding affinity of a compound is. You can rank the compound. This is better, this is worse, and so on and so forth. But here we have enthalpy and entropy. So we can trace a vertical line and a horizontal line through the coordinates of the parent compound. And what happens is the following. Every single compound below the horizontal line will have better enthalpy than the parent compound. Every compound above that horizontal line will have lower binding enthalpy. Similarly, every compound to the left of the vertical line will have better entropy, and every compound to the right, worse entropy. So remember that we know exactly which compound is and where the modifications were made. So with this table or this chart, we know exactly what the affinity and enthalpic and entropic effects of each substitution is. Now, furthermore, we can divide that into 6 different regions or areas, label 1, 2, 3, 4, 5, 6, and each one has a characteristic. So 1 and 2, better entropy and worse enthalpy. They differ from each other because 1 has better affinity. Number 3, everything is worse. Number 4 and 5, worse entropy and better enthalpy. That's the area of the enthalpy entropy compensation. And region 6, better entropy and better enthalpy. So with that in hand, what we are able to do is map a compound or a scaffold and know exactly the type of functionalities that correspond to each region of the molecule. So where polar groups should go, where non-polar groups should go, where polar groups should be avoided because they are going to cause a penalty only, et cetera, et cetera. So the thermodynamic optimization plot basically allows you to do a structure-activity correlation in 3 dimensions: affinity, enthalpy, entropy, rather than 1 dimension, only affinity, which is the classical structural activity correlation. So with that, I can conclude that enthalpic optimization is required for extremely high affinity and selectivity. Enthalpic optimization maximizes the influences of forces other than hydrophobicity and therefore improve LIP-E. And thermodynamic analysis provides a rational strategy to achieve affinity and selectivity goals. Thank you.
A recorded version of this webinar will be archived and available online through the TA Instruments website. We will now begin the question and answer session of this presentation. As I mentioned earlier, please submit your questions through the Q&A window. We will do our best to answer as many questions as possible.